So at the classical level, we have this kind of propagator with the limit epsilon going to 0. This can be seen as the sum of Feynman and anti-Feynman, and it is also the sum of the average of retarded and advanced. Why? Because if you compute the sum of Feynman and anti-Feynman, you get and then you get that. So you just choose. Instead, if you compute the sum of advanced, so this is Feynman, anti-Feynman, the sum of advanced and retarded potentials, then you get something slightly different, because advanced and retarded potentials are obtained by attaching the prescription to the energy only and not the whole p squared, and that is equal to what? 1/2. If you expand that p squared, that is equal to p squared minus m squared plus 2I epsilon p0. Plus 1 divided by p squared. There is an epsilon squared, but that can be neglected because there is already this epsilon and this is already well defined. So it will depend on the sign of p0. Otherwise it is the same thing basically. We assume, of course, that this epsilon is positive, so assume that. And here you have p squared minus m squared minus 2I epsilon p0, and when you compute that, what do you get? 1 divided by p squared minus m squared plus 4 epsilon squared p0 squared, and above you get p squared minus m squared. So it is the same thing because this is also positive. P0 equals 0 doesn't give any problem, because when P0 is equal to 0, that thing can never be 0, so you don't get anything special. Where? Ah, yes, here. So let's see an example of what happens. So that means that in your theory you will have a projection at a classical level. Let's see a very simple toy model which clarifies what's going on. So let me consider a non-relativistic theory So I will denote velocity and acceleration by means of V and A. So this is a Lagrangian. Non-relativistic. Let me now consider a higher derivative version of it, where I add some terms with a higher derivative, so the square of the acceleration. Let us take a simple case. Potential equal to what gives an external force. And then the equations of motion give what? M A plus tau squared A dot dot equal to the external force. So you have an equation like that. Remember the Abraham-Lorentz force, which we already discussed. That gave an equation M A minus T A dot equal to the external force. And you also remember that requiring a smooth limit tau going to 0 allowed us to get rid of the runaway solution, which is the projection we are talking about here. But we had to pay a price, which was precisely the violation of causality. Because in the end, you had this kind of expression, which can also be written in a way that shows analyticity in tau. Well, it's not analytic in tau, it can be expanded. Depends on, that's a smooth tau going to 0 limit. Let's not talk about analyticity in tau. Tau is not complex here. And real analyticity is not that easy, so let's forget about analyticity in this context. And here what do you do? And if you remember, we used to write this as m1 minus tau d over dt a, and then we inverted that operator to the right-hand side and chose that particular green function that was compatible with this smooth limit. And there was only one, no runaway solution, but violations of microcausality. Here, we can do the same, but there is no requirement of smooth tau going to 0 limit, or actually, in the end, it will be like the same, but the requirement is this green function, that is to say, the sum of the retarded and advanced potentials. So this is the unprojected equations of motion, because we have unwanted solutions run away, and if we want to quantize them as phacons, then in the classical limit we will have new classical field equations, which will be a projected one, not this one. And so you write that like this. And then you invert that operator. You can ask yourself, what do you do to invert it? That is 1 minus tau squared p0 squared. We just have the energy here because we only have time. And that's precisely, if you want to multiply by 1 divided by tau squared, so you see it in the other form, p0 squared minus 1 divided by tau squared. So 1 divided by tau squared is the mass. And you have to compute it as the sum of the retarded and advanced potentials. Half sum. So again, if you want, that is 1/2 minus 1/2 divided by 2 tau squared, 1 divided by p0 plus I epsilon squared minus 1 divided by tau squared plus 1 p0 minus I epsilon squared minus 1 divided by tau squared, or you can work it out as the arithmetic average of Feynman and anti-Feynman. It's the same. Anyway, let me write down the result. That you get. This is a straightforward exercise. And what you get is this. I have a sign here, because remember that in the Abram-Lorentz force, you have a sort of friction. This is not a friction, so you don't have really runaway solutions here, because I chose the sign here to be compatible with what we have in higher derivative theories with, let's see, well, this is written in the higher derivative form, but you can also write it with non-higher derivatives, without a higher derivative form, but I'm not sure I have it here. Oh yes, I have it. And then if you do it that way, you will have an object with a negative kinetic term. Just that. Corresponds to what we... to something you have necessarily to quantize as a fake. But you cannot reproduce this case with a Lagrangian, because this is a friction. And the friction doesn't come from a Lagrangian, you know that. It's not a conservative force, kind of. And there is no Lagrangian for that. It would have to be plus there, but then it would have to be non-real. So keep in mind. Anyway, this is it, and if you want, you can prove, if you want an exercise in mathematical methods, prove this. There is a modulus there, so be careful. That's equal to delta of u. So when tau goes to 0, this MA becomes F. F is equal to MA. Otherwise, you have a strongly oscillating factor, convolution with a strongly oscillating function that tells you that basic space and time oscillates everywhere, and the frequency is 10 to the minus 36 seconds. There is a simple way to prove it. And that is cosine u over tau tends to 0. Sine of u times the cosine of u over tau tends to 0 by the Riemann-Lebesgue theorem, which you might remember. And then take the derivative of that, and you get this. So for example, if your external force is Gaussian, that means something. There is a constant, but then we can write MA equals to sort of average of Fx. By that we mean this way to average the force on the past and the future. Then you can plot it in some cases, and you will find something like this. And if tau is very small, you will not be able to feel the difference. But that is what in principle you get. So that is to yes. That is to to illustrate what happens. And what would you have to do in gravity? You would have to take this action to get to the right classical limit. Take the action. And then derive the field equations. Solve those of chi by means of the fake green function. Insert the solution into the other equations. And then, if phi is also fake, repeat the same for phi. So now, just to conclude, I will illustrate how this works with the Friedman-Robinson-Walker metric that you might have already met. That's a simple case. The Friedman-Robinson-Walker case, actually chi mu nu doesn't even enter. You just have phi. And so what you are going to consider makes sense only if phi is treated as a fake itself, because chi mu nu is not. Let me describe what happens there. So this metric depends on just one function, and that function is only a function of time. But this sigma squared is defined here, and in the normal situations, k can be 0, 1, or -1, depending on whether your universe is expanding or will expand forever or will bounce back or in between. Normally, k is assumed to be 0, but we are about to close to 0, but here we don't need that assumption. So So you just insert this into the equations, and actually here we prefer to use the higher derivative form of the action. We can use both. In this case, let me give you the formulas of the equations for this action. And we see what happens when we project them. What do they give? Did you see already the Friedman, the equations for the Friedman-Robertson-Walker metric? Yes, okay, so this will not be a huge change. The unprojected equations, which means the higher derivative equations in this case, are as follows. I will tell you what G is. G is the Newton constant, but it is related to the parameters I've been using in a certain way that I will tell you later. So, some notation. What is G? The Planck mass is 1 divided by the square root of the Newton constant, and that is equal to 8 pi zeta divided by kappa. Zeta and kappa are constants used here. We are at vanishing cosmological constant. Cosmological constant can be introduced later as a so-called vacuum energy, so there is not really a need to use it as an independent term of the action. You might be familiar with that. Can be seen as component of dark energy, so-called. So it may be included into the stress tensor for the matter part, and the matter part here is simplified by assumptions that are made with the Friedman-Robertson-Walker metric, which is that you have isotropy and homogeneity. Isotropy means that you have invariance under rotations, and homogeneity that you don't have dependence on space coordinates but just time. And under that, the matter part, under those assumptions, the matter stress tensor, which has two indices, nu and mu, is some rho, which can be depending on time. So that's the energy density. And then there can be a pressure, P, time dependent, possibly. and that contributes like that. So this is well, the field equations, the equations look like that. Well, these are the usual equations. The modification is that here you get two operators. They factorize remarkably. By the way, with this simple metric, since it is Weyl invariant, the metric is Weyl, not Weyl invariant, has a Weyl tensor equal to 0. This thing does not contribute. This is 0. Does not contribute to the field equations also. You can check it because, well, that can be written as a square of the Weyl tensor. So it cannot contribute if the metric is the ansatz for the metric. That is an ansatz. So a guesswork for the metric. The ansatz for the metric has a Weyl tensor that is identically 0. That's why chi mu nu does not contribute here. That is why there is only r squared, which can be rephrased as the scalar phi. And then the projection of these higher derivative equations makes sense only if we want to treat phi as a fake degree of freedom. So these are meaningful higher derivative equations, classically, because there is no chi mu nu. And if you want, you can just treat it like that. Treat them as having only physical degrees of freedom. But the lucky situation that people are not aware of, apparently, is that the equations factorize these two operators. What are these two operators? Sigma is equal to 1 plus 1 divided by the mass of phi squared, 3a dot divided by a plus d over dt, d over dt. And epsilon is sigma plus 2 divided by m phi squared, k divided by a squared. This k, many k's here, too many. Now this k is this k, but this k is called k. So it's not the kappa here. This is kappa. And this is a kappa. Fortunately, we cannot do much about it. Well, we could go backwards and change the notation, but we can only go backwards in time for 10 to the minus 36 seconds, so no chance to achieve anything. Because no event, as you learn from this, is completed in that amount of time, so you cannot change anything of what you did. So this is good, this factorization, because it is precisely like the factorization we had here, in this case. So you take that and you invert it, and that is the projection. And you have to invert it by means of the half sum of the retarded and advanced potentials. So the projected equations look very much like the Friedman equations, with the difference that on the right-hand side you have averages of rho and p. And the average will be defined by means of sigma or chi. So let me describe them briefly to give an idea, but basically just have this. And you will have to define the average of something with the operator A as 1/2 the retarded Green function plus the advanced one. And they can be, you can talk about retarded and advanced potentials even if they depend on the metric itself, even if they contain functions. They are not just, for A equals 0, this is precisely the operator we had in the simple non-relativistic toy model. That's it. But A equals 0 indeed is flat space. A equal 1, sorry. A equal 1 is flat space, so if you take A equal 1, A equal 1 is flat space if you have K equals 0. This is K. First I have to cancel this. So if A dot and K go to 0, both these operators are equal, and they are equal to the other one. But normally you have to solve these things self-consistently, so the projection is very hard. But there is one interesting case where you can handle it exactly, and I just conclude with that. Oh, by the way, there is also you can also derive from these equations, or the other ones, a continuity equation, which is much simpler than those. And that is d rho over dt plus 3 rho plus p A dot over A equals 0. That can be derived also from the conservation of the energy momentum tensor. So instead of having two complicated equations like those, you can replace them by one complicated equation and a relatively simple one. You can choose the one you want. So there are two complicated equations, but actually there is only one complicated equation there. But there is a simple case where you can solve them exactly, the projected equations, and for radiation, combined with the cosmological constant, which is the vacuum energy density, so-called. Basically, you have this information, radiation, vacuum energy density gives you a relation between rho and p and tells you what is an equation of state for them. And the equation of state of radiation is this. The equation of state of the vacuum energy density is constant. And the equation of the combination is the sum of the two. Well, why is that radiation? Remember that we proved that the stress tensor of Yang-Mills fields of QED was traceless. And therefore, if you want this thing to be traceless, P has to be equal to rho divided by 3. Rho P, P, P. One index is up, one index is down, so in the trace you don't have minus signs, you already have the minus sign in there. So if that is traceless, that is like that. Instead, P equal constant. Yes. The equation of state of the vacuum energy density is actually P equal minus rho. But then it implies that this is constant. These two cases are the only ones you can solve exactly because they are the ones that make one right-hand side vanish. If rho is equal to 3p, this vanishes. If rho is equal to minus p, this vanishes. So you can, that's why you can have an exact solution. The projection becomes very simple. This average becomes very simple because if you have the average of 0, you would have the average of 0, that's 0. It doesn't really matter if you have retarded, advanced, whatever. So that's a case where you can solve them exactly if you want. I can write down the solution. Yeah, 2 minutes. But otherwise, the projection is very, very complicated because it is inherited from the quantum field theory. Quantum field theory is defined only perturbatively. And so you will end up with the classical equations that are only defined perturbatively, precisely as in quantum field theory. And because there is an iteration to make, you see, these operators depend on A, and so these are not actually the finally projected equations, but they are only a perturbative form, and sometimes it's not that easy to make the projection non-perturbatively, because for doing that you would need to know what quantum gravity is non-perturbatively. And normally this is not important, but probably these equations and this non-perturbative issues will become important if we apply the Friedmann-Robinson-Walker solution to the Big Bang. Because if you remember, if you did some cosmology, 10 to the minus 36 seconds around the Big Bang is precisely the duration of inflation. So That's something we are studying now with a student, and we don't know what will happen there, but maybe there is something interesting to see. Okay, thank you very much.